my name is Devanshi Patel. I'm a senior at Wentzville Holt High School, and my research this year was on increasing the efficiency of iron catalyst reactions. Now, catalysts are anything that are used to speed up reactions, and they do that by lowering the amount of energy required to make a reaction go through. You can see them used in the production of many things, including petroleum, cleaning products, and in this case, medication. Now, a recent global problem is trying to make the processes by which we make these medications better for the environment. And as such, recent research has shown that using ferric ions or iron catalysts were actually better for the environment because of their disposable methods and their purification methods, which make it better rather than the second and third row transition metals that are more expensive and toxic for the environment. Now, the reaction in question here also uses a propylic alcohol, which are key ingredients for organic synthesis by way of catalytic hydrogenation, which I will explain next. Now, just kind of looking at the picture of things, what you see on the left here is the actual catalyst that I was working with in part of my project, and it is ferrocenium tetrafluoroborate, which includes the cation/sandwich complex, which is an iron ion in between two organic ligands, which forms a sandwich complex that is positively charged, which is paired with the anion tetrafluoroborate. Looking at the reaction that I was using, which is a propylic substitution reaction, you can see the outline there. The OH is considered a hydroxide, and that the reaction with the primary alcohol and the propylic alcohol actually forms the product as part of the propylic alcohol is replaced with the primary alcohol. And since both of those were kept constant, the product should be the same. Now, the two things that I looked at were the solvent used in the reaction in relation to percent yield, as well as some decomposition studies, so I could analyze the stability of the catalysts themselves. For my product yield procedure, I essentially set up a reaction which I then run and extracted a product, which I ran with gas chromatography, and you can actually see an example of that there at the bottom. Since the products were the same, the product would show up at the same time frame, which you can see here is at about that 2-minute mark. And so all of my data was collected in that manner, in which that peak at the 2-minute is integrated to give me a percent yield, or the amount of the starting material turned into the product. Looking at the decomposition studies, I used time-resolved UV-vis spectroscopy, and if you look at the graph there on the right, you can see it in the orange zone at the 615 nanometer mark is the absorption wavelength of these ferrocenium catalysts. So the absorbance is graphed at that wavelength against time, and that linearized line will give me the rate constant of decomposition to analyze how stable that catalyst is in that solution. So looking at the percent yield data, the one in silver there is dichloromethane, and that, along with the other chlorinated solvent, had about 90% yield, and that is the current standard in the laboratory for these procedures as far as solvents go. But what is really surprising is acetonitrile, which is actually very simple in chemical structure, having almost 100% yield across 3 trials, and that is supported by the fact that its simple chemical structure did not override the catalyst's activity, which is supported by the fact that the 2 heavier solvents, dimethylformamide and dimethyl sulfoxide, had barely 2% yield as their complex chemical structures interfered with the catalytic behavior in the reaction. Looking at the decomposition studies, I ran many different variations, but there's 2 data sets of value, and the 2 at the top there are the same catalyst, but one is in normal dichloromethane, which I mentioned earlier is the standard in the laboratory, and with the same catalyst in the nitrogenated version of that solvent, which is basically just a solvent bombarded with nitrogen particles to make it more pure, the nitrogenated version had actually a slightly lower decomposition rate constant, indicating that the catalyst was more stable in that solution. Looking at the bottom, the catalyst there is actually very complex and decomposes relatively quickly. But when I paired the normal dichloromethane with a variable cosolvent, HFIP, its decomposition rate constant lowered significantly, making it the lowest rate constant of decomposition for the entire data set, which also indicates that that catalyst was made stable with that cosolvent addition. So what all this data tells me is that the usage of chlorinated solvents is is not ideal, but the usage of a simpler solvent actually gives the highest percent yield and could be used to make the reactions more efficient in the future. And as well as the inclusion of a nitrogenated solvent along with a cosolvent can help increase the stability of that catalyst so it doesn't decompose before the reaction runs to completion. Those factors combined can increase the efficiency of that catalyst. In the future, I like to identify ideal time and temperatures as well as running more trials with cosolvents in different alcohols, as those were all kept constant in this experiment. Basically, it all comes down to the fact that simpler solvents along with nitrogenated solvents and cosolvents can help increase the efficiency of these reactions, which makes it better for the environment and thereby reducing the overall cost by which to make the products that are being formed. And by replacing the more toxic metals with iron, the reaction is even made more better for the environment, thereby making production green. I'd like to thank Dr. Ike Bauer and the Department of Chemistry and Biochemistry at the University of Missouri St. Louis for the help with this project. And I'd like to thank Ms. Jennifer Hess and Wentzville Holt High School. These are my sources. Thank you for your time. And if anyone has any questions.
Yes, there are two. Acetonitrile is a solvent that is extremely difficult to remove. Although this may have a higher yield, do you think that the difficulty to remove the solvent, meaning rotary evaporator, is worth the gain in yield?
I actually do, simply because when we're making these products, they're being formed in such high quantities that that taking out that solvent in turn will actually benefit the reaction if we're replacing the solvent used, because if you're getting in these small amounts, it may seem like I'm only getting a little bit more out of the reaction, but in larger amounts, actually going through that trouble will be helpful.
And how do you see these results being used in a real lab?
Okay, so as I mentioned in previously, the reaction specifically that I was using is used in the production of medications. So by replacing some components of these reactions that are used in the production of medications, those processes can become greener and can actually be cheaper for the consumer, thereby reducing the overall cost.
Right, wonderful. Thank you so very much, Devanshi.